synonymous in everyday life. The words mass and weight have different meanings in physics. Mass represents the amount of matter that, that something is made of. I like that definition or that sentence, but there it is. Um, it refers also to, commonly called, is the inertia of something. Okay, how much matter is something made of? Now, it does not refer to things like heavy or big. Okay, so here's a mass balance where you could take objects of known mass and put them over here and balance them with objects of unknown mass to be placed over here. So that would allow you could use that to find out how much mass an object has, a simple mass balance. Now weight, on the other hand, has to do with the force of gravity, and that has to do with where you are, because the force of gravity is different on Earth as compared to places like the moon or in outer space somewhere or Jupiter. Those places you would have a different weight. It represents the gravitational force on an object. Because of the interaction between two masses. We'll see later that that's actually a force between two masses, equal and opposite force by the third law, based on the two masses of the object. But for us, right now, with the weight here on Earth, because we're so small relative to the Earth plays a major factor in that force. So, remember Newton's second law, where the sum of the forces equals ma? Well, for our force of weight, we use Fg. So this is the weight force. The G just meaning gravity, gravitational. And M, instead of just A, we use G. And on Earth, we know what G is. On Earth, G equals 10 meters per second squared. Okay. But we have some other values to consider as well. Okay. Some other gravitational values. Now you could think of these in terms of newtons per kilogram as field strength. Okay. Because there's a gravitational field around the object. It would take a planetary body, and there's a gravitational field around that, stronger near the surface and weaker away from it. So those are just field, the black represents field lines. And that field strength is directed down towards the center of the massive object here, wherever you are. And you could, so not only could it be meters per second, but a Newton per kilogram. And you remember a Newton was kilograms times meters per second squared. So that over kilograms, you can see, just gives you meters per second squared. Okay? So the Earth, it's 9.8. The Moon, for the Moon, so let's do this. Earth, G, 9.8. It could be Newton per kilogram. So the field strength or the acceleration, 9.8 meters per second squared. We would also sometimes say it in terms of G on Earth. So in G's, this is 1G of acceleration. The Moon, its field strength is 1.7 Newton per kilogram, or 1.7 meters per second squared for accelerations, or 0.17 G's. Okay. Now notice that the actual acceleration is 9.8, but in general calculations we use 10. Except in lab we'll use 9.8. Okay. For Mars, we have 3.7 Newton per kilogram, or 3.7 meters per second squared, or 0.38 Gs. Now, you could look up the rest in your reference table, or not the rest, but more examples in the reference table. Okay. Now, G isn't all 9. It varies across the surface of the Earth based on the mass that's beneath you, and they actually use variations in G to look for like heavy mineral deposits because of the mass. There's a lot of mass in things like lead, and if you're looking for that, you'll see variations in the acceleration due to gravity. So they look for variations to find that. They're small variations, but slight variations on the surface of Earth as well. Okay, here's an example. What is the weight of a 60 kilogram person on Earth? Moon is the second question. Well, on Earth, the formula Fg equals mg. The weight force is just the mass of the person times g, or 600 newtons. Okay. Now pounds is also a weight force. It's just different units than a newton, but you can convert a newton into pounds. And then on the Moon, the weight on the Moon, put that there, still 60 kilograms. The mass doesn't change, but the acceleration due to gravity does. And 60 times 1.7 is 102 newtons. Now you could use a scale like this to measure force. Sometimes they, or many times, they have mass on one side and force on the other. But the mass part of the scale would only work where it's calibrated. So if it's calibrated to masses on Earth, yeah, well then you can use it. But if you brought the same scale to the moon, then this would not be working properly. So when you take a weight or some object and put it on there, the weight due to gravity is going to be down, and it's going to pull on a spring that's in this, and it's going to stretch that spring down a certain amount. But it's based on what the weight of the object is, the amount. Okay, so we're going to be talking a lot about equilibrium and objects that aren't under any net acceleration. Okay, coming up in the next few topics, or the next few sections.